Hi everyone, in this video we study the E2 elimination reaction. Elimination reactions come in two forms, E1 or E2. However, the basic conditions that we will study in this video favor the E2 pathway. E stands for elimination, and 2 stands for bimolecular, the fact that two molecules are involved in the rate-determining step. We'll study more about that aspect of the reaction in a later video on the mechanism. There are 3 criteria that must be met for an elimination reaction to take place. First, there must be a beta hydrogen, that is, a hydrogen at the beta position. The alpha position is defined as the carbon bearing that leaving group, X. X we're treating as a leaving group. And we would label then, from the alpha position, the beta position, which is next door. There can be more than one beta position, and a hydrogen attached to the beta carbon is what we are referring to as a beta hydrogen. The second criteria is that we must have a leaving group, and a good one. Good leaving groups are very weak bases. Halide ions like chloride, bromide, and iodide are excellent leaving groups. We'll also see some others, the tosylate and the mesylate. And finally, we need a strong base. Alkoxide or hydroxide bases are commonly used for elimination reactions. R is representing a generic alkyl group. So it could be methyl, ethyl, propyl, isopropyl, tert, butyl. And that base is paired with a metal ion. Group 1 metals like sodium or potassium are quite common here. The product of these reactions are alkenes. And for the purposes of keeping track of our atoms here, the beta hydrogen ends up on our alkoxide base as a neutral alcohol or water byproduct, and our leaving group pairs up with our metal cation. The alkene is the product of interest here, and these other components of our product are simply washed away in our workup steps. Let's look at a few examples to understand the regio and stereochemical outcomes for the E2 reaction. In our first example, we are dealing with a tertiary alkyl halide. That is, the alpha site is connected to 3 carbon groups. Thus, we name it tertiary. In our reagents, we're dealing with sodium methoxide in methanol as the solvent. Our reactive species here is the methoxide ion. Anytime we see a metal ion, we're just going to ignore it. It's our counter ion, a spectator. Remembering that what's left over is anionic. So we have our strong base and our alkyl halide. If an elimination reaction were to take place here, how many alkene constitutional isomers would you expect to be produced? We would expect 2 constitutional isomers to be produced in this reaction. First, we need to look at the beta carbon and see if there are beta hydrogens. There is a pair of beta hydrogens at this position, and eliminating one of those would give me this alkene. If I look to the other beta position, there's a trio of beta hydrogens here, and eliminating any one of those would give me this alkene. And finally, we have a beta position up north, which eliminating any one of those would yield this alkene. So if you guessed 3, that's not far off, but you may have forgotten to consider bond rotation, which would show me that these 2 isomers are in fact the same. We have 2-methyl-butene just drawn differently by rotation about this single bond. What we observe from our experiments in lab is that a major product is produced here. The more substituted alkene is isolated in larger quantities compared to the less substituted alkene. And we determine the substitution of an alkene by counting the number of alkyl groups at the 2 carbons of the double bond. In our major product, we have 1, 2, 3 alkyl groups, so this would be a tri-substituted alkene. In our minor product, we just have 2 alkyl groups, so this would be a di-substituted alkene. Zaitsev's rule, named after Alexander Zaitsev, a chemist who studied elimination reactions in the 1870s, states that the more substituted alkene is the major product. His rule is based only on his experimental evidence. He didn't know why the more substituted alkene was the major product. As we've come to find out, the more substituted alkene is the most stable product. So why is a more substituted alkene more stable? Well, it has to do with a concept known as hyperconjugation. This is an inductive effect where these alkyl groups are donating a bit of electron density into that sp2 hybridized carbon. Why would sp2 hybridized carbon want more electron density? Well, as s character increases for a hybridized orbital, going from sp3 to sp2 to sp, that atom becomes more electronegative. So donating electron density towards a more electronegative atom is going to be stabilizing. Thus, having more alkyl groups on an alkene will be more stable. One way that chemists can alter the product distribution is by changing the base. Here we are using potassium tertiary butoxide. If we ignore the potassium ion, we are left with the T-butoxide ion, which is similar in basicity to methoxide, only much larger. TBU stands for tertiary butyl, and if we draw it out, we see that this back end is much, much bigger compared to methoxide. As a result, it's too hindered. It is too large to get in and abstract a proton at the more substituted site. So the faster process and easier process is to take a proton from the less substituted site. That makes the less substituted alkene the major product when we use a bulky base, such as potassium tertiary butoxide. Based on these experimental results, is the E2 reaction regioselective? Yes, this reaction is regioselective because we produce the more substituted alkene in excess of the less substituted alkene when the base is small. When we change that base to a bulky base, such as tertiary butoxide, now that base is sterically hindered and can most easily abstract a proton from the less substituted side, yielding the less substituted alkene as the major product, one constitutional isomer in excess of the other. What we find when we carry out this reaction in the lab is that our more substituted alkene is again the major product. And while the trans and cis isomers could be envisioned here, it is the trans isomer that is produced in excess of cis. So because we produce one stereoisomer in excess of another, the A2 reaction is characterized as stereoselective. So why is that trans alkene produced in excess of cis? Well, it has to do again with stability. These two alkyl groups are far from one another, whereas in the cis configuration, the two alkyl groups can sterically interfere with each other if they are large enough. So trans is more stable and produced in excess of the cis isomer. There are cases where the cis isomer will be produced as the only product, and we will study those examples in a later video along with the mechanism. As we saw in our tertiary example, we can also tweak the conditions to favor one product over the other. By using a bulky base, tertiary butoxide again, we can favor elimination at the less substituted site. With a bulky, sterically hindered base like T-butoxide, we also virtually eliminate the possibility for a competing SN2 reaction. The large base is a poor nucleophile. It can't get in and displace that leaving group. In our final example, we look at a primary alkyl halide. Primary alkyl halides have only one beta site. There is a set of beta hydrogens here. And that simplifies things because only one elimination reaction is possible here. In order for an elimination reaction to dominate with a primary alkyl halide, we must have a strong base and it must be a sterically hindered base. T-butoxide is perfect for this. It is too sterically hindered to substitute this alkyl halide. If the base is small, like methoxide in methanol, we will get as the major product the substitution product. It forms much faster than the elimination product here because getting in and substituting this leaving group is easier than coming in to the forest here and deprotonating one of those hydrogens. Overall, the E2 reaction is regioselective. We form the more substituted alkene when we use small bases such as hydroxide, methoxide, or ethoxide. When we switch to a bulky base, such as tertiary butoxide, we can then produce the less substituted alkene as the major product. The E2 reaction is also stereoselective. Stereoselective means that one stereoisomer is produced in excess of the others. Quite often, the trans stereoisomer is produced in excess of cis. However, there are cases where the cis product is the only product. We will study those examples as well as the mechanism for the E2 reaction in other videos. Thanks for watching.